Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 4.4 from your textbook, which is discussing the idea of a span of a set of vectors. The first thing we're going to be doing in this video is we're going to be proving this theorem right here. We already mentioned this theorem in the previous video. We said that, even though we define the span of a set of vectors to just be a set, it's not really just a set. It is actually a subspace. It is a closed vector space. So we're going to go ahead and start by proving that that is actually the case. So after that, then we'll look at a couple more examples about really trying to understand what the span of a set of vectors is. Does a set of vectors span a known vector space? And if not, what sort of space is it spanning? But to start with here, let's go ahead and talk about this theorem. So this theorem says we've got these vectors, v1, v2 through vn. So we've got some set of vectors in some vector space v over some field f. And what we're going to try to prove here is that the span of those vectors is not just a set, but it's actually a subspace of v. So, of course, what this means is if we need to show that it is a subspace, that means we need to show that it is closed under scalar multiplication and vector addition. So we need to show span v1, v2 down to vn is closed under vector addition and scalar multiplication. So, as usual, let's go ahead and start with the under plus here, right? So, we're going to start with closure under plus. Okay, so let's we've already used the notation of v1 through vn, so I don't know, let's use w's here. So let's let w1 and w2 be elements of the span of v1, v2 down to vn. So what we need to show then is we need to show that w1 plus w2 is an element of the span of v1, v2 down to vn. Okay, so we're going to start with these two vectors that are in the span, and we're going to try to show that their sum is in the span. All right, so what does it mean for these two vectors to be in here? Well, since w1, w2 are elements of the span of v1, v2 down to vn, then w1 must be something like c1, v1 plus c2, v2 plus cn, vn. In other words, w1 must be some linear combination of v1, v2, and vn, with c1, c2, cn all just being constants. And of course, w2 must be very similar, must be like k1, v1 plus k2, v2 plus kn, vn, with of course c1 through cn, k1 through kn, all elements of your field. Okay, so that's what it means for these guys to be in the span, right? Is that they are linear combinations of these n vectors. Okay, so then let's take a look at what we can say about w1 plus w2. That would be c1v1 plus c2v2 plus cnvn plus k1v1 plus k2v2 plus knvn. Now, that's w1 there, that's w2 there. Let's group this according to these vector 1, then vector 2, etc. So we can see this then as c1v1 plus k1v1 plus c2v2 plus k2v2 plus plus cnvn plus knvn. And then we can do a little factoring here, right? We know that we have the distributive property when we're working inside of a vector space. So we can actually go ahead and factor these guys and write this as c1 plus k1 v1 plus c2 plus k2 v2 plus plus cn plus kn vn. Now, that actually is good enough, right? Because if you recognize this, c1 plus k1, c2 plus k2, all the way through cn plus kn, all of those are constants. So this tells us that w1 plus w2 is a linear combination of the v1 through vn. So w1 plus w2 is a linear combination of v1 through vn. So w1 plus w2 is an element of the span of v1, v2 down to vn. Check. So we've gone ahead and we've shown that this thing is closed under addition. Okay, I think we'll go ahead and do the scalar multiplication on the next page. So we'll go ahead and do that here. So let's go ahead. Now we need to do closure under scalar multiplication. So we're going to let W be an element. Oh, we can use W1, I suppose. Let W1 be an element of the span V1, V2 down to Vn. And we're going to let K be an element of the field. What we need to show is we need to show that KW1 is an element of the span of V1, V2 down to Vn. So again, since W1 is an element of the span of V1, V2 down to Vn, then W1 is equal to some linear combination C1 V1 plus C2 V2 plus plus Cn Vn, of course with those C1 through Cn elements of the field. Okay, so that's what W1 must be equal to. Well, then KW1 must be K times C1 V1 plus C2 V2 plus Cn Vn. And we know that we have the distributive property that this distributes onto all of those. So we can view that as KC1 V1 plus KC2 V2 plus KCN Vn. And then just with a little bit of sort of parentheses for notation, we can see that as KC1 V1 plus parentheses KC2 V2 plus KCN Vn. Each of these, KC1, KC2, KCN, all of those are constants, so this is a linear combination. So KW1 is a linear combination of V1 through Vn. So KW1 is an element of the span of V1 through Vn. Check. So what does that tell us? So span V1 through Vn is closed under addition and multiplication. So span V1 through Vn is a subspace of V. So when we talk about the span of a set of vectors, it's not just a set of all the linear combinations, it is actually a subspace. And this really tells you guys that coming up with the span of a set of vectors is an easy way to sort of generate different types of vector spaces, right? If you want to come up with an interesting vector space, you just pick a couple of vectors from some space and think about everything that is generated or spanned by those vectors. And that'll always be a subspace / vector space. Okay, so this tells us that the span is not just a set, but actually is a subspace. So to finish this section up, right, let's go ahead and take a look at a couple more just sort of examples of understanding the span and whether or not it spans known vector spaces, etc. So to start off with, though, let's just think about what we can say about the span of a set of vectors. Okay, so here's a set of vectors. Each of these guys is a matrix in the 3x3 matrices. And what I'd like to do here is I'm not going to ask whether or not these generate all the 3x3 matrices. Instead, I want to just try to describe what types of matrices are spanned by these guys. So let's think about what we can say here. So if we take those sort of matrices, or these vectors here, the span of these guys, so the span of these matrices, 0, 1, 0, negative 1, 0, 0, 0, 0, 0, comma, 0, 0, 1, 0, 0, 0, negative 1, 0, 0, comma, 0, 0, 0, 0, 0, 1, 0, minus 1, 0. Well, what is that going to look like? Well, that's going to be the subspace where you take a linear combination of these things. So it would sort of look like anything that can be written as C1 times the first guy plus C2 times the second guy plus C3 times the third guy. Now, I think at this point, and these are just brackets to represent that this is a set, right? It's not just a single element, right? It's a set of all things that look like this. Now, I think we've done enough work with sort of matrices that we should be able to very quickly put together what these guys look like, right? This C1 goes here and here, C2 goes here and here, C3 goes here and here, and if we combine all that stuff together, it looks like we'd get the 3 by 3 matrix that sort of looks like 0, C1, C2, negative C1, 0, C3, negative C2, negative C3, and 0, if we combine all that stuff together. Okay, so that right there is the sort of span of these three vectors, right? It's the matrices that look like this. But can we say a little bit more about these matrices here? I mean, this is a good description mathematically. It's saying anything that looks like 0, C1, C2, negative C1, 0, C3, negative C2, negative C3, 0, right? So if you pick C1, C2, and C3, these guys must be 0, and these guys over here must be the negative of those elements there. But you guys actually know what these types of matrices are, right? These are all the skew symmetric matrices, right? These are all the ones where when you take the transpose, you get the negative of the matrix. So what we've actually just realized is that this is actually the set of matrices such that A transpose is negative A, with A an element, of course, of the 3 by 3 matrices, right? Which, again, this right here, these are just the skew symmetric, the 3 by 3 skew symmetric matrices. So in other words, what we did here is we examined what types of things can be built out of these, and once we had sort of done that as a general element, we realized that this is just a way of describing the 3 by 3 skew symmetric matrices. So this right here is what would be called like a generating or spanning set, not for M3, but for the skew symmetric matrices in M3. Okay, so this is just to show you guys that, it can be interesting to examine the span of a set of vectors, even if it doesn't span the overall vector space. It can span a sort of interesting subspace, in this case, the skew symmetric matrices. All right, let's look at a couple more examples. All right, so now we're going to sort of combine what we've been doing into a single question. So we're going to try to determine if these vectors, 2, 6, 1, 7, 3, 1, all of these guys are in R2. We're going to try to determine if they span R2. So are these three vectors a spanning set for R2? If they're not, then we're going to try to describe what they do span. So now we're sort of combining what we did in the previous video, where we asked, is something a spanning set for an overall vector space, with what we just did in the last example, where we said, well, maybe it's not the entire vector space, maybe it's just an interesting subspace. So we'll try to first determine if these guys span all of R2, and then if not, we'll try to describe what they do span. Okay, so we want to know, do 2, 6, 1, 7, 3, 1 span R2? Okay. You have some serious grammar issues here with whether or not that should be does these span R2 or do these span R2. But either way, it sort of sounds awkward, but that's okay. We're math, not English here. So let's go ahead and get this done. So we want to know, do these guys span R2? So in other words, right? Right? What we need to do is, does C1, 2, 6 plus C2, 1, 7 plus C3, 3, 1 equals, well, what does the general element in R2 look like? AB always have a solution. In other words, that's our question. Because remember, that's what it means to span. It's saying that anything in R2, anything, right, any AB, can that be solved in terms of something times 2, 6, something times 1, 7, something times 3, 1. Okay, we can turn that into a system of equations. That looks like we should get 2C1 plus C2 plus 3C3 has to equal A. That's all the first components. And then we should get a second equation that is 6C1 plus 7C2 plus C3 equals B. If you want, you can then put it into an augmented matrix form, 2, 1, 3, 6, 7, 1, AB. Now, remember, we're not going to actually solve this. Instead, we just want to know, is this a consistent system? We don't care if it's a unique solution or infinite solutions. We just care, are there solutions? So let's go ahead and study whether or not the rank of A is the same as the rank of A augmented. So to do that, we'll do our standard sort of operation, R2 replaced with R2 minus 3R1, 213A, and then it looks like we should get 0, 4, negative 8, B minus 3A. Okay, there we go. Actually, that's good enough. This tells us that the rank of A is going to be 2. I mean, I didn't divide by 2 up here and divide by 4 here, but I could. The point is that there's 2 pivot positions, so the rank of this is going to be 2. But the rank of the augmented part is also 2, because there's only 2 rows here. So this is going to be, this system will always have solutions. Technically, it actually is always going to have infinite solutions because you have a rank of 2 and you have 3 variables, so it's going to have infinite solutions. But again, we don't really care. We just care, does it always have at least one solution? So it does. So what this tells us, 2, 6, 1, 7, 3, 1 do span R2. In other words, you could say that the span of 2, 6, 1, 7, 3, 1 is equal to R2. So either phrasing is fine. You can say that these 3 vectors span R2, or you can say that the span of those 3 vectors is R2. You might be asking yourself, how do I know that the span isn't something even more than R2? Well, they can't be anything more than R2 because they live inside of R2. Each of these is just a vector in R2. So the most they could possibly be is R2. So we are sort of using that as a background piece here. Okay, so that was sort of interesting here, right? We sort of took 3 vectors, examined if they spanned R2, found that they did, and then we're able to say, well, that must mean that their span is all of R2. Let's try that again. All right, so we'll work in a slightly more interesting vector space. We're going to work in P2 of R. So this is going to be the polynomials of degree 2 or less. We want to determine if these 4 polynomials here, x squared plus 1, 3x, negative x squared plus x minus 1, and 4x squared plus 4, whether or not those span P2 of R. If not, then we're going to need to try to describe their span as best as possible. Okay, so to answer this, right, what we need to do is we need to consider, does the following always have a solution? So if we take C1 times the first polynomial, plus C2 times the second one, plus C3 times the third one, plus C4 times the fourth one, 4x squared plus 4, is that going to always have a solution for the general element of P2 of R? What's the general element of P2 of R? It would look something like ax squared plus bx plus c. Okay, so we go term by term using like terms here. In terms of x squared, so it looks like we're going to have a c1, negative c3, and 4c4, and that's going to be a. So that's going to be our first equation, c1, technically plus 0c2, since there's no x squared term here, minus c3 plus 4c4 equals a. Then for the x term, there's not going to be anything here. There's going to be a 3c2, a 1c3, and nothing here. So it looks like that should be 0c1 plus 3c2 plus c3 plus 0c4, and that's going to need to be b. And then finally for the constant terms, looks like we should get a c1, nothing here, negative c3 here, and 4c4 there. So c1 plus 0c2, what do we say, minus c3, and then plus 4c4 has to be c. Okay, so there we go. Let's go ahead and write that more in a standard form that we like, which is to put it as an augmented matrix. So 1, 0, minus 1, 4, 0, 3, 1, 0, and 1, 0, minus 1, 4, and then A, B, C. Okay, so again, we're just curious, is this thing going to be always consistent? We don't care if it's unique solutions or infinite solutions or whatever. We just care, is it going to be consistent? So let's do our first operation here. R3, replace it with R3 minus R1. 1, 0 minus 1, 4. 0, 3, 1, 0. And those have A and B. And then here we should get 0, 0, 0, 0, and then C minus A. Okay, so right here, this is a big concern. We have a 0 row here, but we don't have a guaranteed 0 value here, right? This will have no solutions if C minus A doesn't equal 0, right? So if C minus A is not 0, then this thing has no solutions. So, well, obviously C and A can be anything, so there's no guarantee that this is going to be 0. So that tells us that these guys do not span P2 of R. So x squared plus 1, 3x, negative x squared plus x minus 1, and 4x squared plus 4 do not span P2 of R. In other words, there are some polynomials, specifically ones where this doesn't equal 0, that they do not span. So we cannot say that these 4 polynomials span P2 of R. Okay, now let's try to figure out, right? In the last video, we sort of just ended at this point. We just sort of said, okay, it doesn't span P2, so we're done. Let's move on to the next one. But this time we're going to say, well, since it doesn't span P2, what does it span? How can we describe the span of these vectors? Now, I want to do this in sort of 2 ways. I'm going to first do it just like we did earlier in this video, sort of by brute force. And then I'm going to return to what we did here to sort of see that we get the same conclusion. So let's see if we can describe the span, right? So what is the span? Okay, so we know span of x squared plus 1, 3x, negative x squared plus x minus 1, 4x squared plus 4 would be the set of all things that would be C1, x squared plus 1, plus C2, 3x, plus C3, negative x squared plus x minus 1, plus C4, 4x squared plus 4. So that's a little sort of smaller, but there we go. Now we can erase that and just make it a little cleaner. Just scoot everything down a little bit. Okay, so again, the span here is anything that can be written as C1 x squared plus 1 plus C2 times 3x plus C3 negative x squared plus x minus 1. That is a minus x squared there. And then plus C4, 4x squared plus 4, anything that can be written like that. So let's sort of simplify that and describe that a little bit further. What that is that's the set. Well, what sort of things do we get for x squared? Well, we get C1, negative C3, and 4C4. So that looks like we would get something that looks like C1 minus C3 plus 4C4 x squared. And then looks like we get plus, what do we get for x? Looks like 3C2 plus C3. So we get 3C2 plus C3 x. And then finally, we get plus C1 minus C3 plus 4C4. Okay, now, this is incredibly sort of messy because of all these constants. But there should be one thing that sort of jumps out to you right away. What we have here is exactly the same as what we have here. So what if we sort of re-parameterized and we didn't use these sort of messy definitions of C1 minus C3 plus 4C4? Notice no matter what we choose, this is always going to match this. So in other words, if we re-parameterize, right, we should recognize this as the set of all things. I don't know, let's just give this a name. I'll call this T, I guess. Tx squared. Now this is certainly different, so I'll call that S plus Sx. And then this is exactly the same as this, so plus T. So in other words, it's all the sort of quadratic polynomials that have this property that what their coefficient for the x squared is is the same as their constant. So this would be a nice description for the span of these vectors. Now, could we have sort of realized that this was the description from back up here? Well, yeah. If you think about it, this was saying that it had no solutions if c minus a wasn't 0. So what if, we want there to be solutions. So that would mean that c minus a does need to be 0. Well, c minus a being 0 would mean that a and c need to be the same. So if a and c are the same, that's exactly the type of polynomials that we just described. So in other words, what we're sort of saying here is that this collection of vectors, x squared plus 1, 3x, negative x squared plus x minus 1, and 4x squared plus 4, they don't build everything in P2 of R, but they build this subspace of all the sort of quadratics that look like the coefficient of x squared and the constant match. So they build sort of a unique subspace of P2 of R, but not the entire space of P2 of R. Now, if you're a little unsure about how we did this reparameterization here, don't be too concerned about that just right now. This is sort of lucky that we just recognized this. As we go further on, we'll recognize how to do these sorts of reparameterizations to better understand the subspace, because we'll sort of know how many parameters we will actually need. So right now, I just sort of did this as an example for you guys, but we'll learn some better ways of doing it later on. Okay, I think we had one sort of last example here. We want to try to see if we can reverse the sort of logic that we've been doing here. So far in all the examples, we've been taking sort of sets of vectors and then trying to figure out what does their span look like, or do they span some big vector space. Now we're going to flip it around. We're going to look at a subspace and try to think of the generating spanning set. In other words, we're going to try to reverse this logic. All right, so for our last sort of example here, we're going to consider the set S of matrices that have the property that A equals A transpose. So in other words, they are symmetric. And they also have the property that their trace is 0 and they are 3 by 3. Now, I'm going to just state that this set is a subspace of M3. If you guys want some more practice doing proofs of subspaces, closure under addition and closure under scalar multiplication, you can try proving this separately. This guy here is not only just a set, but he is actually a subspace, meaning if you add two things, they will remain symmetric and their trace will remain 0. And if you multiply it by a constant, it will remain symmetric and its trace will remain 0. That's basically a short verbal proof of why it is a subspace. All right, what we want to do though is we want to find a set of vectors that spans this subspace. So we'd like to come up with a way of building this off of some small set of vectors. So how do we do this? Well, let's think if we can sort of describe the general element in here. So S here, in this case, is the set of all matrices A, such that A equals A transpose, and trace of A equals 0, and A has to be 3 by 3. Okay, so let's see if we can start to describe that. So it's the set of all matrices that look like what? Well, let's think about that 1, 1 position. Well, can I put anything I like there? Sure, it's the first element, should be pretty safe. I'll put an A. Okay, now what about this 1, 2 element? Well, this doesn't impact the trace, so I can probably safely put anything I like right there. So let's go ahead and put a B there. Now, that doesn't have any impact on the trace because it's not on the diagonal, but it does have an impact on the symmetry. We need A to be A transpose. So that means if I place B here, I also have to make sure that I have B right there. Okay, what else can I do? Well, let's look at that 1, 3 element. This guy doesn't impact the trace, so I'm pretty safe in just putting whatever I like there. So let's put C. But of course, we do need it to be symmetric, so if I put C here, he also has to go over there. That guarantees the symmetry. Okay, let's go to we've already figured out the 2, 1 element. Now let's think about 2, 2. Well, there's 3 things on the diagonal, and they have to sum up to 0. I've only put 1 value there, so I'm safe in putting whatever I sort of like right there. So let's put in D right there. Now, as soon as I do that, remember, these 2 things plus whatever's going to be here has to be 0. So that means that this 3, 3 element has to be negative A plus D, because we need the trace to be 0. All right, last element right here. This guy doesn't impact the trace, so I can put whatever I like. I'll put E. And then, of course, because it's symmetric, I have to put E right there. So those are the sort of types of matrices that actually are going to build all the matrices that look like A equals A transpose and the trace of A is 0. So now let's think of a spanning set of these. But it's really easy to get a spanning set. You're just going to let each parameter be 1 while all the other parameters are 0. So let's go ahead and do that. Let's actually now look at this as it can be the span. Well, let me start by letting A be 1 and everything else be 0. So that would be 1, 0, 0, 0, 0, 0, 0, 0. But since I chose A to be 1, I would have -1 right there. Okay, next one. Well, I would let B be 1, everything else be 0. So 0, 1, 0, 1, 0, 0, 0, 0, 0. Okay, now do the same thing. Let C be 1, everything else be 0. So that would be 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. Sorry for the dog drinking water in the background. I don't know if that's going to pick up on the video, but he's quite loud. All right, now we've got, we're going to let D be 1 and everything else be 0. So 0, 0, 0, 0, 1, 0, 0, 0, -1. And then finally, we're going to let E be 1 and everything else be 0. So 0, 0, 0, 0, 0, 1, 0, 1, 0. So these 5 matrices, their span will be all of the things that look like this, which is the same as the set S. Now you might be asking yourself, okay, why do we let each thing be 1 and everything else be 0? Because it's a very easy way to make sure that this span is this. If you think about it, if I want to build something that looks like this, all I need to do is A times this guy, B times this guy, C times this guy, D times this guy, and E times this guy, and then just add them all up. Because the way we sort of did this is we made sure that this guy gave us the components with A, this guy gave us the components with B, this guy gave us the components with C, and this guy gave us the component with D, and this guy here gave us the components with E. So these guys will guarantee to span this, which is the same as the set of all symmetric matrices that are 3 by 3 and have a trace of 0. All right. In the next video, what we're going to start investigating is linear independence and dependence. And I do want to give you guys sort of a brief preview of that. The preview I sort of want to do is I want to go back to this example here, where we had these sort of 4 polynomials, and we were investigating whether or not they span P2. What I want you guys to sort of see here is that there were a lot of vectors, but they ended up only spanning these very special polynomials. And that's sort of weird, because there were a lot of things here, yet we were sort of limited in what we can build out of them. And the thing I want you guys to recognize is that some of these pieces weren't really contributing very much. If you think about it, this 4x squared plus 4, he wasn't building anything that we couldn't already build with this guy, right? Why do I know that? Well, because 4x squared plus 4 is just 4 times this. So if I can build something out of x squared plus 1, I can also build it out of this guy. So he wasn't really contributing anything. Over here, right, if you think about this guy is actually built out of a combination of these. If I do -1 of this and 1/3 of this, I build this. So this guy wasn't contributing anything. So the only 2 that were really contributing were these 2. And we're going to investigate that idea of contributing by a concept called linear independence. It turns out that these 2 vectors are what we call linearly independent, but these 4 are linearly dependent. It is not a coincidence then that in this set, we could have reduced it to 2 linearly independent vectors, and our reparameterization involved 2 parameters. So we'll be investigating that in our next video.